Hello. Okay, hello everybody. We are very happy to present our work today. And we are going to talk about the runtime we have been working on, which our project tries to work on the VM of the Smalltalk, and our work has reached a point where we started thinking about if we really need a VM. So I think you know here and Javier know how to present them. So well, our work is on VMs, but we work on Smalltalk. We are developing a VM in Smalltalk, and we have presented our work in previous Smalltalks, and we reached the point where we started thinking why we need to have a VM in Smalltalk. Okay, this is a huge hypothesis, and we started thinking what are the things that the VM leverages. So, well,
for our work we use this previous approach.
It works in the approach.
Okay. So we leverage on some. Sorry?
No, myself.
Bueno, perdón. Okay. So to build our VM, we use a leverage from some host VM. So we leverage on basic object, method lookup, primitives, and native helpers. For basic object like true, false, nil, and character, this is a small piece of code from the shitter. So we say load true, and it actually moves some address to EAX, which is the receiver. So basic object work more like tags. So we tag EA true is this address. We don't do actually anything with true. We just compare with this address. Also, we leverage on method lookup. Every object has a method dictionary array, and so this is for the selector multiplexer, which is like a bit polymorphic inline cache static. So we compare the method dictionary for every class, and again we use the method dictionary as a tag. Also, when we don't have the actual implementation, we leverage on the host VM method lookup. So we say, okay, we don't know how to solve this message, so please host VM solve it for us.
The host VM is the VM where we run our code. Our code is already in Smalltalk. And until we have a VM written by ourselves, we use another Smalltalk. So that's what we call the host VM.
Yeah. And this is for everything except when using a full closure, which means just put everything in a closure, in a set which is closed. And this is the case for the garbage collector, which was presented 2 years ago in Quilmes, I think. And so, also we have primitive. We haven't implemented all the primitives, so for some primitive we just say, okay, please host VM, solve this primitive, and give me the answer. We don't want to implement the primitive. And some small native helpers which actually don't look like object-oriented. This is not the case, but you have small pieces of code written in the virtual machine that we need that. So I will say, okay, host VM, implement that small piece of code. This is something important, because We do that because we want bit-to-bit compatibility. So we want to generate the same code as the original VM. And to do that, we have to use the same helpers. But, okay, who does need bit-to-bit compatibility? Probably we don't. So we want to start afresh. How to start afresh? Okay, with objects. We have this B library. B is the name of the smalltalk we are building. I don't know if anyone knows, but here's the name. Sorry, it's okay. So we have this B library, which is a fragment of the image in a file. This is something before us, something that is used, and we are going to take it. So we take something that is called the smalltalk kernel. This is the fragment that we do care, and we are going to put there some native code. So here we are talking about objects. Everything is object, which is different than the host VM when object was stored in some place called a code cache. Well, I don't know if it was called a code cache, but we call it a code cache. Now we have native code as an object, and we modify the compile method to actually point to this.
Remember that we have a JIT that generates native code that we presented some years ago. So we are using that here.
Yeah. So we have the native code, which has some code, which is a byte array, and references. Code looks like this, which is a byte array with a lot of bytes, but it's actually assembly. To understand this, we need, the cheater actually generates this. And it's not bit-to-bit compatibility with the host VM. We change the layout and we do some fancy things. We want to do more fancy things. And this is like the next. Yeah, okay. So we have references. And the references, because when you cheat, you have some references to objects outside the code, like classes, literals, the compile method. You reference the compile method from the code. So all those references we are in the references array or collection. Okay, so we need to connect method just to run. So we implement lookup and invoke. And if you see the yellow box, that's the code generated when you do a message send. It just push some. You move the receiver to EX and you push the selector and call to lookup and invoke, which is implemented in Smalltalk. You just check if you can look up a symbol to self, which is the one that has to solve the problem, and if you can't find a compile method you send does not understand, and if you found a compile method, you just transfer control to the actual implementation. Here is the lookup, which only takes a method dictionary, and you have optimization for small integers because you have literal, which is just a tag address, so you have to take the small integer method dictionary. But once you have the protocol, you do a lookup in a protocol. And this is to implement linear lookup. We can implement something better, but this is working, and probably we are going to change it as soon as we can.
The framework this is very simple linear lookup, so it's a dictionary. But the framework allows you to change the lookup algorithm. So if you just go and change this method and regenerate everything, you change the lookup algorithm.
Yeah, we need something really simple to understand if something goes wrong, where is the problem. So we don't want to make optimization which are natural to do, but we are not going to do that now. Okay, so we have block closure. As Tudor said today, block closure is something complex. It's not trivial.
Okay. What we are seeing is the implementation of a primitive. Okay. One detail about the previous stuff. It's some little thing I wanted to say. This is implemented in Smalltalk. Okay. You are doing the lookup in Smalltalk, so there's a bit of a detail because if you want to do lookup in Smalltalk, your lookup is going to need to do a lookup. Okay. You may be wondering, how do you fix that problem? Okay, if your lookup does lookup, you fall in a recursion and you never end. So we have to be a little picky and say, okay, this is the lookup, these are going to be the methods involved in lookup, and we are going to take some care of them. We are going to nativize some special bits so that the lookup doesn't actually call itself recursively, because that wouldn't work. Okay. Now going back to the block closure, the value primitive is it's a primitive that is relatively simple, because you only have to look for the compile method for the block native code and execute it. There's not much. Everything that is involved in evaluation a block is done actually by the bytecodes, but most things are done in the bytecodes when you enter the compile method. So evaluating a block is just taking the address of the native code, pushing the arguments, and calling. Okay. So here we are just transferring control to the code of the block. Okay. And well, we are seeing here a value marked, which is a very similar implementation of value, but which serves other purpose. And when you want to do an ensure, you have to do something, because the semantic of ensure is that I want to execute this block that I'm passing as a receiver, but I also want to execute this other block. Okay. So this other block has to be executed if the block ends naturally without a return, or if the block returns from the method. But if you imagine how is the stack when you are returning from the block, you first created a stack frame for the method, then you did some other things, then you have the block, okay, and now you are going to return from that block you are going to remove until the called method. Okay, so you have to remove a lot of stack frames, and before doing that, you have to take care of executing the ensure in the process before that. So the way to do that is to mark the stack. Okay, when you are going to execute an ensure, you mark the stack. You say, okay, here is something special. When you return from a block, you are going to return until here, and then you are going to stop. And if we are going to execute something special, and then we are going back to whatever we were doing. Okay.
No. Wait. You can see there that we are verifying the native stack, so we can access to fields that are meaningful in the Smalltalk implementation. We know what a receiver, where the receiver is, and we can call it, name it, receiver, we can name the compile method and everything from the stack.
Yeah. I was talking all that before because we were going to see this, and this is implementation of the return from block. Okay, so there is another important detail here, that you are seeing a block in a return from block. Okay, so you again have to take care of recursion and to not fall into an infinite recursion. So here actually the blocks are not full closures, are just jumps. Okay, so the compiler has to be smart enough to optimize these blocks so that we are not using blocks when we are implementing something relative to blocks. Okay, because if we did that, it wouldn't work.
But you could, if I understand, this is only when the block has a return.
Yeah.
So you could still use blocks.
We could still use blocks that don't have a return.
But here is while false and
Yeah. Well, actually, we could remove this because we are after the return from block. The return from block smashes the stack. Okay, it removes everything from the stack. So this return is not going to be found because we are, before finding the code for the return, we are going to jump to a red return. Okay, we are actually going to see this in the next slide. Here in the bottom we see the implementation of drop upper context returning, and here what we are saying is that we are going to drop a lot of context. Okay, and we are passing the result, and also we are passing the amount of arguments we have to pop. Okay, because we have to also pop the arguments that were passed to the block we are returning from, or I can't remember if it was the block or the method. And volví un poquito para atrás.
Just one little thing. Okay, we see some assembly code here. Again, we are trying to keep the minimum amount of assembler code. So this is like, okay, we do have some, but it's like minimal. We try to be minimal always.
And also the assembler doesn't have processor-specific instructions. The final instructions are, of course, processor-specific, but what you see here is like pop R, which is pop receiver, push receiver, restore temp. So if you wanted to port this assembler to another architecture, you wouldn't have to modify all the callers to the assembler. You should only modify the implementation of these assembly instructions, like pushing the receiver or popping the receiver. And one thing before is that you can see here that we are verifying the smalltalk frames, okay, the stack frames. You can see in the line that says, the third line says frame bframe current. Okay, we are creating an object there that represents the stack frame in the top of the stack. So we are going to move to look for the stack frame where we have to return. The implementation, there's a lot of code, but you have to check if you find the 0, that means the stack ended and you didn't find anything. Or if the frame has a block, you have to do some checks, or restoring some state. Or if the frame has a marker, you have to stop and return to that point and not from the block, from the method. But the interesting thing is that if you see what was before this, the return block bytecode was a call to some cross VM function. Okay, it was implemented in assembly, and here what we do in that bytecode is to send the message return, _return, okay? So the bytecode return from block gets nativized to something that says send message return, and that's all. Okay, we are introducing the minimum amount of assembly as possible.
So we need to create objects, and to do so we are going to add some arena. We are not adding a garbage collection, we are just creating object there, which is enough for us. So we add primitive new, and it's just allocation on some space. Okay. Also we have we want to call some libraries. It is important.
Okay, and we also wanted to implement this without much assembly. So what we did is to, when we are nativizing the primitive 94, which is the primitive for sending a native call. If we see the native call, un poco más para atrás. Una más. No lo tenemos. Bueno. Okay, if we see the method that has the primitive, it's okay. It's in the first one. This gets translated to a method that in the first bytecode says I am a primitive, so you have to nativize something special. So the nativizer, when it's got to prepare the frame, sends a message again. So this is not implemented as assembly. We are sending a message, and in the message we are trying to do whatever is necessary to translate every object into the bytes that need to be pushed in the stack. Okay, so what do? We make a byte array of the size of all arguments together, and after that we start sending to each object that was received by the method that is an API call. We send the message, we want to marshal you as some kind. Okay, you can see that in the last lines. Marshal as type into arguments at next. So we are saying you have to put your representation as, for example, an unsigned long in that position of the array. Okay. In the end, what we are going to do is to take this array and expand it in the stack. So after that, we can only do a call to the native function. This ended to be a really cool way because it's really polymorphic. You are going to say, Neil, I want to marshal you as an unsigned long. Okay, Neil says, put a 0 at that offset in the arguments array. But if you put true, it says, okay, put a 1, or you put false, put a 0, you put a byte array, put whatever it is put, okay? Otro más.
Okay, so we add to this library, which is skernel, some primitives like perform, which actually was very straightforward to implement, because perform with no argument is like do a lookup and transfer control to that. We have already implemented that. To implement perform with argument, we had to send a message to array to expand into the stack. That was kind of tricky, but it was straightforward. So we implement FI, symbol, hash, string, comparisons. But here is some magic, because we took this library and we add some P5 property, and now we have some skernel.exe, which is a P library self-contained with almost everything in Smalltalk, and actually does run. So this is how we do create everything. We create we have some level builder, and we add true, false, nil. We add some minimal kernel classes, a lookup, primitives, arena, some other things. We are going to, okay, we say one kernel initialize, just start. For example, we have some tests that we do run in the library. So we build this bkernel.exe, and we can say, okay, run this test using command line. Okay.
Let's try it. If I can find them out.
Está bien, no, estaba abriendo.
Está en SBTest.
Necesitaba cargar el execute test, run test. ¿Lo abriste nuevo? Sí, el cluster browser. Sí, hace falta. Se da mucho garabato.
Alguno que relate.
Relata. Okay, so what we are going to do is assert the correct execution of the test, which means run the process and check the result. If the process doesn't crash, that can mean that the test didn't fail. And
actually, we do check, and we do return 1 in the case that everything is okay, 0 when everything, if anything fails. So it's not like run or
So we're going to try this.
okay, so what it's doing is to generate the kernel, so you only see that the test passed.
It took some time to build the library in the background. Somewhere over here.
You're running it again from the console.
That's the library that is just generated. And it's actually an executable file, if you can see it. You can tell. That means it's executable. And this is Linux, that's why I'm using Wine, but it's just a straightforward Windows executable.
Tienes que decir el nombre del test.
For example, we're going to run all the tests. No, run all of them.
Sí.
And it just run all the tests. It's the same executable file that was generated. And, well, that's one example. I could probably add...
that's one example.
If I can add something like a delay, so you see that it changes when we regenerate it, for example. Run test, guys. So I could do delay, but if we use delay, I have to go and add the delay class to the exe we have generated. So we're just going to do it a bit simpler.
Sí.
Huh? No,
sí.
That's a quarter of a second delay. Now, I'm going to try, but it's not going to work, but still. I just run it once, so it generates a library. It didn't work, but it needs sleep. You see there, it says sleep, it's missing. So something changed. So we have to go now and generate an add sleep to the library we're building, so you see how we do it.
Kernel library builder to browser. Build kernel builder. No, build library builder. Es un trabalenguas. Add minimal kernel. Busca minimal. Methods. Right.
Here we have all the methods. Today it's a manual process to add stuff. It's not really, not fully manual. Like there is some tree walking to generate the objects, but some of the methods need manual integration.
Actually, we are creating a minimal kernel that is smaller than the S kernel because it's faster to test. It takes like 5 times, I don't know, 5 times more to generate the complete kernel. So we want to have something that is smaller.
So we add sleep to the list, and then you can try again.
The file is locked.
Sorry?
The file was locked, that's why it's not moving.
Okay. It just tried to write the exe, but the exe was executing, so it couldn't write it because the file was open. That's what Toller said. So now we run it again, and it's a bit slower. So it is working, right? You can.
So we can add, for instance, support to native multi-threading. So we can run all the tests, but concurrently. Just can you check that?
Yeah, we changed the collect here to run all the tests for concurrent collect. That's here. And basically, it's the same implementation as collect, but it forks for every index or every element in the array, and then it waits until the answer does not include the token. That's the initialization. So it's some very lazy way to know that the collect is done, like all the elements in the array have been done. Okay, and then fork thread sends value on a new thread, and this is how it's done. It uses a Windows function to execute the code for value on the receiver. Okay? And we have another...
All concurrent.
Yeah.
All concurrent. All concurrent.
We have another method exported. They run all fast, apparently there's one that's taking a while, or something, I don't know.
Probablemente haya muerto.
This is without the delay, right?
No, it is with the delay.
It is delay.
It's all concurrent.
But the delay is for
Right, the
every
delay
test.
is still there, it's the same code. I didn't generate it
So
again.
it's like...
It's multi-thread, it's native multi-threading.
So it's how many threads?
It's as long as the Windows doesn't return error,
Yeah.
it's alright.
So you keep adding threads?
There's one per element in the array.
Okay.
And the blocks finish very soon. But, okay. And there is also something else we can do, like send these to a file. We can compare here. I don't know what's going to happen. We can see if the order is the same. Since it's concurrent, maybe the order changes. Let's see.
In order to
Oh.
Terminó. Okay, there are quite some differences in the order. Screen ads, I don't know, it's here, okay. There is a difference. So, the order was
One is the serial and the other is the key.
yeah.
Okay,
What happens
Pastor.
when you have a pretty large collection and you keep adding threads?
Probably it will fail sometime. Yeah, we have to work on
Let me
that.
see. There is no error checking.
Yeah.
So,
Okay.
some of the elements won't be collected.
Okay.
Maybe that's what happened. On the first time we ran it, it didn't finish. It can't there. It didn't finish like this. We never saw it before. Maybe that's what's happening. So one of the blocks didn't get evaluated. So one of the elements in the collect was never executed.
So-
It was never collected. So, it never finishes.
Okay.
So since there is no error checking,
Okay.
Sorry, but beside those details, this is very important because the host VM does not support native multi-threading. So we are avoiding the cost of pre-file the stack and doing the process switching. We don't do that.
yeah, our intention is to implement the green processes in Smalltalk using native threads.
Yep.
And maybe if it's too hard, then maybe the threads won't run concurrently, but we still use the facilities of the OS to support the multi.
Use fibers in the OS, it's not spinning.
Okay, then we're thinking of using fibers in the OS. No, that's a great advice. That's a great advice. But if we can, we keep running concurrently. We'll see how far it gets. So there are some details that we need to solve.
So here's the only thing that is actually protected, which is the creation of new objects. You have to take care of that because a lot of threads are going to try to create new objects. But that's the only thing.
Yeah.
Yeah.
When you usually run multi-threaded applications, you have to be careful that they don't clash, right? And this is the only place where we added locks.
Yeah, it's interesting because we can control basically everything. Okay, this is the biggest advantage, I think, because we have no barriers. There's no VM that we can't modify. If we want to see the code and check it and see if we could make an improvement, we just do it. In this case, we detected that was the only problem that seemed to be the only problem. We still are having issues and we could improve a lot, but we saw that this was the only problem to having a multi-threaded implementation for some little things. So we said, okay, we place mutex here. That's the only problem. Okay, let's check. Worked. So that's really, 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 really amazing.
So we are working on kernel libraries and debugger. We need some kind of debugging. I don't know if you want to say something.
It's just a little thing how it works. The idea is that when you issue a halt, you send halt, the implementation spawns a new process that attaches to the debuggee, and the debuggee then gets halted by the debugger, by the OS, and then the debugger can inject some memory to communicate and pause the main thread and create new threads to evaluate things, to do back traces and.
So we need garbage collection, cheater, promoting, and probably in some future performance, REM, and that's it.
Yes, for the break.
Sorry, can you say?
What do you have in the kernel right now?
What we have in the kernel? Yeah, actually we have a project that is the smalltalk kernel that has, I can't remember the basic classes. It includes streams, it includes class objects, collections.
Es unit.
It's the unit.
No, it's a unit.
Y lo
No.
pusiste.
Sí, it's unit.
Yes, kernel.
Some reduced version of it's unit.
It's not in the kernel, but we already integrated.
Yeah, but collection basically. Collection object.
Yeah.
True, false. A nil.
Number.
Nil.
The less that is possible actually.
And some cherry picked method or classes. Anything else?
All right, the multi-threaded stuff. Do you have it currently running with garbage collection? Or
No garbage collection. We think that we want to implement stop the war and collect. Like D8, well, it's very common actually.
A few years ago, we presented some sort of multi-threaded garbage collector, but that was a stop the war, and the GC was multi-threaded. So it was not like for a multi-threaded VM. But we have some ideas we want to try.
Yeah, yes, but we don't want to do promises. We want to do code and then show them. No?
Well, my question was, pretty much about multiple threads, because I just want to say that I don't really think that the only place when you have to synchronize is the allocation. But if you don't have a JIT, then yeah. But actually making the JIT working with multiple native threads, that's the tricky bit. That's the tricky bit.
Yeah.
We'll see.
I
hope we get to the point to have those problems.
Yeah.
It makes sense. What you're saying makes sense. The truth is that there is a lot of code that's static in normal programs in Smalltalk, like the libraries and that stuff. And we want to take advantage of that. So for that, we're gonna pre-generate the native code that we're doing with the JIT, and then let the JIT run. Maybe we have to do stop the war and JIT. Maybe. We just don't know now. Yeah.
And the second point, when you were talking about this lookup stuff, that's maybe an idea for you. A couple of years ago, I did a similar thing for a different VM, and I ran into the same problem. Like, if you customize the method lookup, then the method lookup itself in Smalltalk might need the method lookup. Right?
Yes.
The method regarding.
Yes.
First, I did exactly the same that you did, and then later on I figured out that way too limiting. So the possible way how to get out of it is to maintain the state of these, activated methods. And if you detect a recursion, then just short circuit it. But still you get a bit more room to send the things.
We actually have when the JIT is not devising and gets to a send, we have some sort of pluggable send bytecode JITing, and we have different implementations. One implements a call to the lookup, another one just uses a static method. So for a symbol, it knows what compiled method to use.
Okay.
And so we have, it's not like they are hard-coded, really, is that they are from a set that will not require a lookup because they are not polymorphic, pretty much.
Or we use the polymorphic inline cache, but static, so like a multiplexer. We use that.
Like we use a set of compile method that can respond to this selector.
Yeah, I got it.
That's what we're doing.
Thank you.
Thank you.